welcome to Physics 105. As usual, I'm going to start with the class, and I'll try to finish early so that if you guys want to leave, you can leave. If you want to ask questions, you can ask questions and we can discuss for a little bit more. Let me share my screen. This week, we'll continue with chapter 3 of Giancoli, Kinematics in 2 and 3 dimensions, and we'll describe vectors. So here's your reading assignment, if you like, and these are the suggested problems. I think I'll have time to solve these problems maybe tomorrow. If we go too quickly, I may solve one or two today. So we started with introduction, measurements, and scientific methods. And then last week we started with like simple one-dimensional motion, and this simple one-dimensional motion in constant acceleration, i.e. the gravitational field, like Galileo did. And now we'll do the same thing, but in a more general geometry. So, okay, let's start. So kinematics in 2 and 3 dimension is actually what we see every day around us. And for example, if you are watching snowboarding, or if you are doing snowboarding, this kind of jump is actually very characteristic, right? And there's like, you can see the effect of gravity. And then how do we describe this? How can we mathematically express this kind of motion? Or if you look at these water flows under like this fancy light, you also see same kind of geometric curve, like a parabola. Here's the fireworks, the same thing, and more. Or like if you want to do parachuting, and say if you want to jump off the cliff, and of course you don't want to fall on the bushes or trees, you want to fall on the ground. For that you have to be able to calculate where you are going to go, and then for this you have to account gravity and your kinematic motion, which we'll show how to do. For like sports, the same parabola. Or if you like basketball, the same parabola. You may have to master your shooting this way, so on and so forth. So how do we describe this of duration, and how can we make predictions? And for this, we need some mathematical machinery, and that is given by vectors. And we have to talk a little bit about vectors so that we can describe such motion. So vectors, we actually have introduced vectors last week. And just to repeat, vectors are special quantities that have both magnitude and direction. Since they are not like ordinary numbers and they are special quantities, they deserve a special way to be added and subtracted. So let's just give a few simple examples and warm up and wake up on this sentence. So for example, you can imagine yourself starting from the origin like this and walking 8 kilometers to east. And then, I don't know, you take a rest and then you walk another 6 kilometers. So these are all both vectors. And when you're here, you can ask yourself, what is the net displacement? What is my net displacement from the starting point? And for this, you add these two vectors. Vector 1, 8 kilometers. Vector 2, 6 kilometers. Your resultant displacement is 14 kilometers to east. So you could do the opposite thing. You could walk 8 kilometers and you change your mind. You reverse your direction and walk 6 kilometers to west. And then you can ask the same question, what is the net displacement? in this case, it's not plus, and it is 8 minus 6, which is 2 kilometers to east. So you can see in one case we use plus sign, in the other case we use minus sign, and we said, oh, these are vectors, we'll come to that. So this simple addition works for the 1D, but it does not for, like, say, in a more general situation like 2D. Now imagine you are walking like this in the second figure. You walk like 10 kilometers to east, you turn 90 degrees north, and then walk like, say, 5 kilometers to north. Of course, in this case, you cannot do anything like this. Like D1 plus D2 is equal to net resultant. It is not. And it is a little bit more general. And for this, we use this kind of notation. We have like D1 vector. We indicate D1 is a vector with an arrow on it. And plus D2, again, the same thing. There's an arrow on it. Is equal to dr, which is also an arrow. So I will show you. I think you already know how to do this, but I think even if you didn't know, you could see your net displacement with a little bit of geometry, right? So here you need two things, like I said. So you want this net displacement, and net displacement is a vector, so it requires magnitude and direction. For direction, you need to calculate this angle. That's going to give your direction, and it's actually simple geometry. Like theta, if you look at theta, you can calculate tangent theta, for example, is equal to, like, let's call this, I don't know, d2 magnitude divided by d1 magnitude. And if you take the inverse, that's what you get. Theta is inverse tangent this side divided by this side. And if you do this with your calculator, you'll find 27 degrees. So you found the direction, and now you need to find the magnitude. And for this, you can use Pythagorean theorem. And it's like basically some simple algebra, and there you go. You have the result. Of course, if we have like more complicated cases with many vectors and more general geometries, of course we can do this, but we don't want to do this over and over again. So we have some rules for vector addition. So let's go through them. So there are actually more than one way, but I will explain the first one, tail to head method. So for this, you start with drawing the first vector d1 with an arrow and to scale. I mean, the direction and scale matters, and you draw your vector to its scale. For example, where can I do this? Like, maybe I can draw here some orange. Okay, let's say this is my d1. And now draw d2 similarly with its magnitude and direction, but place its tail to the tip of d1. So this was first one, and we place the tail to the tip, like say this is my d2. To find the net resultant vector, draw an arrow from the tail of d1 to the head of dr. And here is your sum. From the tail of first to the head of second. This is dr. So this is how we sum vectors. You can use this, where there is also like a parallelogram rule. Maybe I can also quickly show you if you'd like that way. Actually, maybe I can do this. I don't want to draw erase. If you do parallelogram rule, delete this guy. So I'll basically, in the second case, we put tail to tail and head to head. So this is, I just transported this vector to here. And now I have D2, and I think I can erase this. They are the same vectors. And for the parallelogram rule, we draw the parallelogram, draw a parallel to this one on the tip, draw a parallel to this one on the tip of the other, and here is my resultant vector. And you can check it is the same. So there are a few things that we need to go through in vector addition that are nice. First, the order of addition does not matter, right? If you add V1 to V2 or V2 to V1, you'll get the same result. So we say vector addition is commutative. So if you have 3 vectors, you can add any 2 first and then add the third, like V1 plus V2 plus V3, or V1 plus V2 plus V3. And we call this vector addition is associative. So we can show this with examples. Maybe I can erase this and do it again. Let's start from the beginning. So let's see. For example, I can start with this guy. Okay. Copy, paste. So this is the first one. This is the copy. This is the second one. So I'm using this head to tail. I'm adding one by one from head to tail, and let's take the last one. Copy, paste. Okay, now what is my net sum? Total displacement from the tail of the first to the head of the last. And here's my result with red arrow, maybe DR. So let's do it in another way. I don't know, maybe I can start with this guy. It actually doesn't matter, but let's just do and see. Paste, okay. Maybe a little bit like this. Maybe this way, copy, paste. And copy, paste. Okay, you can see these seem to be completely different drawings, but let's see the net resultant vector from the tail of the first to the head of the last. Okay, and DR. Now we can look and compare if these two guys are the same. This one and this one, they seem to have the same orientation and the same length. So vector addition doesn't matter, which is kind of nice. Okay. So once we have addition, now we can speak about subtraction. For this, we have to define negative of a vector. Given a vector v, we define minus v as the vector which has the same magnitude but opposite orientation. You just flip the vector. You put the head where the tail is and you put the tail where the head was originally. Then the vector subtraction is defined as v1 minus v2 as v1 plus minus v2, like this. Here's the example. Let's zoom in a little bit. So v2 minus v1, v2 is the same. We reverse v1 and make plus. You can see this is minus v1. And you can use this head to tail method, v2 minus v1, and here's the difference. I think sometimes some people can be confused, but if it's like this, or just step by step go through this and then faithfully apply your head to tail method, and you'll get the right result. One more thing, how do you multiply vectors with a scalar? Suppose you have a number C, and if you multiply V with C, the result is a vector which has the same orientation, same direction, but its magnitude is C times larger. That's the definition. All right, now we can move on to okay, these are like a little bit technicalities, but they are useful. So adding vectors via components. So given a vector, you can decompose it in its perpendicular components, right? Suppose you have a vector like this, which is V. You can express this vector in terms of these perpendicular components, Vx and Vy. And if you were in three-dimensional, more general geometry, you could also add Vz too. But now I wanted to keep drawing simple. And notice that in this notation, Vx and Vy are also vectors, but these are vectors along special directions. For example, you can calculate what the magnitude of Vx and Vy are. So when, I think maybe I should say this one more time. So when we have arrow on the letter, it means it's a vector. When we delete arrow, it's like this. What we mean is the magnitude of the vector. Like Vy is the magnitude of, so Vx without arrow is magnitude of vector Vx, and same here. So the question is, what is this? You can, like I showed in the first page, you can just use geometry, and geometry tells me it is magnitude of V times cosine. So you can be confused sometimes with a cosine sign. Cosine is generally the closest side. So if you think of this triangle, cosine is the closest side, divided by, of course, hypotenuse. Sine is the further away side, divided by cosine close. If you want to memorize this way, that's fine. And next, what is Vy? Magnitude of V, oops, maybe I can, okay. Magnitude of V times sine theta. And finally, you can do it again, Pythagorean theorem, to find the length in terms of X length and Y length. So this is useful because if you have a vector addition, you can add them by component. Here's the example from your book. You want to add V1 to V2. What you do is decompose V1 to V1x and V1y. Decompose V2 to V2x and V2y. And resultant vector is this, and you just need its components. Its y component is V1y plus V2y. Its x component is V1x plus V2x, like here. Okay, let's maybe. So here's an example, an exercise, if you like. An airplane trip involves 3 legs with 2 stopovers, like here. And the first leg is due east for 620 kilometers. Second leg is southeast 45 degrees, like this, for 440 kilometers. And third leg is south of west with 53 degrees, like this, for 550 kilometers. 1, 2, 3. So what is the plane's total displacement? Like this vector, what is this? Maybe I can give you a few minutes to warm up. You can, I know it's simple, but it's going to warm your calculational muscles a little bit so that you'll be ready for hard problems later. So the question is here on example 3. There are, the plane makes 3 trips with 2 stopovers with D1, D2, D3. And like directions are given like this. The first one is like this. The second one is 45 degrees. Third one is like 53 degrees. Magnitudes are like this. We are asked to calculate the plane's total displacement. So for each one, I'm going to calculate D1x. I'm going to calculate x and y components. I think D1x is already given. This is to east 620 kilometers, and D1y is equal to 0. D2x is equal to the magnitude, which is 440 times the cosine of this, which is nice because cosine and sine are the same, so we don't have to worry about it. So I just quickly do this. 45 cosine times 44 kilometers is equal to 231. 231 kilometers, and D2x, which is rather nice, the same thing, 231 kilometers. And D3x, now I'll do the same thing with 53. Let's clear this up.
Shouldn't it be D2y, not D2x for the second?
Oh, yes, yes, thank you. Yes, oops. That's correct. D2y, yes, thank you. So this D3, 53 cosine, clear up, 53 cosine times, what is the magnitude? 550, 550 is 331 kilometers, and D3y is equal to, clear this up, 53 sine times 550, give 439 kilometers. Now I have to pay attention to the signs. So D1 is positive 0, D2 is positive in x and negative in y. It's like minus. D3 is negative in both x and y. So this is minus, minus. Now resultant vector D, let's call it drx. Let's sum these numbers. 620 plus 230 minus 331 is equal to 519 kilometers, and D resultant vector y is equal to 231 and 439 670. Now we need to calculate two things, right? First, the magnitude dr, which is equal to squares of this, 519 squared plus 670. Was that right? Yeah. Squared square root. So I can do this too. Clear this up. 519 squared plus 670 squared is equal to, and I want square root of this is equal to, I found 800 something. 847. We have to look at your book. dx2, okay. Yes, thank you. Yes, dx2x should be 311. dx2, this one, right? How did I find that? Okay, let's see. That's a good thing. dx2. Oh, I multiply with the wrong 440 times. Okay, I don't know. Cosine 45. Cosine times 440. Yes, 311. I will blame the morning for this. Okay, this is 300. This is 311. Thank you guys. This is 311. And now I can 620 plus 311 minus 331. This one seems to be 600. And this one seems to be, I think I don't need a calculator for this. So this is 0.58 kilometers. Is that correct? I hope so. And now let's fix that guy. 750, sorry. Yes. At least I'm glad you guys are checking. I would feel really bad if I was doing this whole thing myself. Not bad, but it is nicer this way. This is 600 squared plus 750 squared. Let's see. 600 squared plus 750 squared is equal to square root. Yes, 960. How about that? All right. 960 kilometers. And I need also this theta because I'm looking for a resultant vector. I need both magnitude and direction. So for this, I think I can use tangent. This divided by this is maybe, yes, 550 divided by 600 is equal to, and I need the inverse tangent of this guy, tangent to the minus 1. Seems like I found 51 degrees. Theta is tangent to the minus 1, 750 divided by 600, which is equal to 51 degrees. Hope that's okay. Any problems? Anybody spot? Yes, minus 51, if you like, yes. Like, or I can say 51. I think the way your book says is minus 51 degrees north of east, oh sorry, south of east. South of east. I think we can move on. So let me introduce maybe a couple of more things. So the unit vectors, so we can actually, for a given coordinate system, define unit vectors like this. So in three-dimensional geometry, x, y, z, we have unit vector along I, x, y, and z. And they are defined as being vectors, and their magnitude is unit like 1. I hat is equal to j hat is equal to k hat. They're all equal to 1. Once you have this, you can write any vector like this. V is equal to Vx I hat plus Vy j hat and Vz k hat. And you can see this Vx does not have arrow because we put all directional information to this guy. Now we care about magnitudes. For example, you can do the summation. Again, I showed you in the previous page, say V1 plus V2 vectors. And you can write V1 as V1x I hat, V2y j hat. Same for V2, V2x I hat, V2y j hat. And if you do the summation, you have a parenthesis in front of I hat, it's like V1x plus V2x. And you have another parenthesis in front of j hat, it's like V1y plus V2y. I think this is all we need of vectors. And now we can talk about vector kinematics. Imagine you have like a problem like this, and your particle or object is moving on a curve in, let's say, in 2D, and it's like at P1 at T1, and it's at P2 at T2. So we can do what we did last week. We can define displacement as delta R. Now it's like a vector, and it is R2, your vector at T2, minus your vector at R1, R2 minus R1. And if you do this unit vector decomposition like I showed you, it's like delta R vector is equal to x2 minus x1 I hat, y2 minus y1 j hat, and z2 minus z1 k hat. So once we have this, we can talk about average velocity like we did last week. Del R vector, del t, and instantaneous velocity is defined as the limit where this delta t goes to 0. You can do the same thing and the same result. You have the derivative, first derivative. But here there is like a little bit different interpretation. So now you have this path of object, and the first derivative is generally the tangent vector. Let's draw this. For example, if you're interested in the vector of the speed at point P1, it is like a tangent, like tangent here, like this, and you just put the vector, which is basically this guy, okay? So another example, if you were to calculate velocity at P2, it's also tangent. Let's do this. Just put some tangent line and you put the vector, and this is velocity at P2. And you can do this decomposition for velocity too. V vector is dx dt I hat, dy dt j hat, and dz dt k hat. Okay. From velocity, we can do the same thing for acceleration. We first calculate average acceleration, change in velocity divided by change in time, and instantaneous acceleration where delta t goes to 0. A vector is this, and then it's of course again the derivative, but it's the derivative of v. We can do it component by component again, dvx dt, dvy dt, and dzy dt. And if you use the result you've just found here in the first step, first derivative of velocity is the second derivative of position, and you can do this, dx squared by dt I hat, dy squared by dt, and so on. So here's an example. Maybe I can zoom to problem and then, because I feel like guys already know this, but so the position of a particle is given as a function of time with this, some a times t plus some b times t square I hat plus some c minus some d t cube j hat, where r is in meters and t is in seconds. What is the particle's displacement between t is equal to 1 and t is equal to 2 seconds? We can go through this real quick. What is the particle's displacement between t is equal to 2 seconds and t is equal to 3 seconds? For this, I need to calculate particle's position r1 and r2 at t is equal to t1 and t is equal to t2. Okay, this one is t2. And at the first one is 2 seconds. I just put 5 times 2 seconds plus 6 times 2 squared, which is 34 meters. And for the second one, R2Y, I have 7 minus 3 times 2 seconds cube. And it's minus 17. So basically R1 is 34. Maybe I can write this as like 34 meters I hat plus minus 17 meters j hat. I did this yesterday, but I think it's correct, but I may have some mistakes. You just be careful. So let's calculate R2, the same thing, but we'll put t is equal to 3 here and here and here. And if you do this, I think this is the result. So basically R2, maybe I can write R2 here. Push this a little bit. R2 is equal to 69 meters I hat plus minus 74 meters j hat. And if you calculate R2 minus R1, it's basically 69 minus 34, which is 35. Is that correct? Yes. And minus 74 minus 17, which is like 57. So that's your net displacement. So B, determine the particle's instantaneous velocity and acceleration as a function of time. Maybe I can delete this and do it again. Maybe not. Maybe I can just, this doesn't look that complicated. So for instantaneous velocity, I just take the derivative. So derivative of this guy, 5 times t is 5. That's the first one. Plus derivative of this guy, this 2 goes in front, makes this 6, 12, and decrease the power by 1. It is like 12.0 meter per second squared times t times I hat. This is the direction of the first one. So if you take the derivative of this guy, it's 0 minus 3.0. If you take the derivative 3 times 3, 9 minus 9 meter per second cube times t squared. There is no, I think, so this is, yes, I see your question. So this is so that, you know, you have like meter per second cube here, and you multiply it with time cube, which is like second cube. So this second cube and this second cube cancel, so that you have like a 3 meters as expected, because this is like a distance. So it is not a unit of anything. Of course, it is a unit, but it's not acceleration or anything. It's just dimensions work if you have that dimension for this constant. So there's nothing to worry about it. Okay, so V is like this. I also keep this here. You know, it's like, for example, this is meter per second now, and there's no t, so the unit of velocity is meter per second. So here, meter per second cube times second square will give you meter per second, which is the unit of v. So the question is also asking the acceleration. If you take the derivative of velocity, you have the acceleration. It's basically derivative of this guy is gone. Derivative of this guy is 12.0 meter per second square along I direction, and plus, let's take the derivative of this guy, 2 goes in front, it's minus 18, yes, and it's meter per second cube times t. So in C, evaluate V and A at t is equal to 3 seconds. We just plug in this one to here and here. And if you do this, V is like 41 meter per second along I direction minus 81 meter per second along J direction. And acceleration is, okay, this is a little bit cluttered, but sorry about that. A is equal to 12.0 meter per second square along I direction and minus 54 meter per second square along J direction. So we can plot, for example, V at t is equal to 3, something like that. I had to squeeze in yesterday for this, but it's okay. So I think now we can talk about motion with constant acceleration in a more general 2- and 3-dimensional space, like the pictures I showed you in the beginning. So I just want to remind you, in the last week, we had things like this. Motion in 1D under constant acceleration. We had like these nice 4 formulas, like x is equal to x naught plus v naught t plus 1/2 at squared. And you had v is equal to v naught plus at. And you have this nice formula. If you eliminate t, v squared is equal to v naught squared plus 2ax minus x naught. And if you want average velocity, it's something like this. So the question is, can we write these in a more general 2- or 3-dimensional space? And for this, we assume a is constant. And what this means is ax is constant, ay is constant, and az is constant. You basically take this guy and convert it to vectors. You just put arrows on the top of everything except t. V vector is equal to v naught vector plus a vector times t. And you take this guy and then convert it to vector. Then it's like r position as a vector is r naught plus v naught t plus 1/2 a t squared. So for this one, it's a little bit more complicated. You have to do it component by component. But for this, you need to look at the components of this guy, for example. Vx is equal to v naught x plus atx, or vy is equal to v naught y plus aty. Now you can write the same thing for components. Then you have something like this. So Vx squared is equal to v naught x squared plus 2ax times x minus x naught, and same for y. That's correct. Thank you. So let's go back to our Galileo experiments. And here we can now start with a simple experiment like this. Imagine you have 2 objects falling off the cliff. Object A is falling directly below the ground, like vertically, whereas object B is given a kick. So it's got like a initial velocity. And the question is, under like constant gravitational pull, what happens? And Galileo's observation was objects A and B reach the ground at the same time. So you can actually do this experiment if you have your, I think you can use your cell phone's camera and you can do something like this, right? You can, maybe you can even try with this. You can say, okay, I'm dropping, you can just drop some object and record it. And then later you go back to your video and look at the instance and calculate the distance. Maybe you can even put like a meter stick and then compare the distance with that meter stick. And the upshot is, yes, this you can verify experimentally. Red ball here, and then yellow ball here, you can see at any instant follow each other and they reach the ground at the same time. So the next complication is like, how do you do projectiles like this? So you shoot something with some angle, and how do you describe this? So in this case, you decompose V into Vx naught and Vy naught. And you can see Vy naught is subject to this gravitational pull, so its magnitude is decreasing. And when it reaches its top point, Vy is 0 there, and then from that point on, it reverses direction and it reaches the ground. Whereas the horizontal velocity is constant the whole time. So one last thing before I think I have one more topic, but so I told you this projectile motion is a parabola, and actually we are in a position to show this. So you can write x and y components of this motion, right? X is equal to x naught. X coordinate is like some initial x naught plus Vx naught times t, like how your position along x direction changes. And y is this simple gravitational motion. Y is equal to y naught plus v y naught t minus 1/2 gt squared. So you have two equations, and you want to eliminate t here and here and here in favor of x and y. So you can just do this, and if you plug in, you have something like this. You can see these are constant, some linear in x and some quadratic in x. And here's, if you like, you can do this exercise for yourself. If you do open the parentheses, collect the terms, you have something like a plus bx plus cx squared, and you can find a, b, c. And this is the equation of a parabola. Okay. Y is equal to a plus bx plus c squared is a parabola. So that's why projectile motion is a parabola. As we talk about velocities and acceleration, and now we'll talk about relative velocity. Now, here's how it works. Imagine you're going on a train with some velocity, let's say 80 kilometers per hour, like say east. And you say to yourself, what's my velocity? It's your velocity with respect to a point on a fixed spot on the ground. We say your velocity with respect to Earth is 80 kilometers per hour. Now you could, or like your friend could be going in another train in the opposite direction with the same velocity. Again, with respect to Earth, right? It is according to like a stationary observer on the floor like here. But that's not all we could do. We could also ask the question, what is your velocity on this train according to your friend? That's the relative velocity. If you are A and your friend is B, you say, what is my velocity A with respect to B? You can see from here, this linear geometry is like 80 plus 80 is 160 kilometers. Or if these both trains are going in the same direction, let's say this guy is going with 90 kilometers, this guy is going with 75 kilometers. And in this case, speed of A with respect to B is, okay, this minus this, which is 15 kilometers. Here I want to highlight this convention, how we write velocity, okay? Relative velocity, you just write V of your choice symbol, and we put the arrow to say that it's like a vector. And the first subscript is the object we are interested in, velocity of A, how fast A is going, and B is the reference frame, if you like. So the way we read this, velocity of A with respect to B. Always stick to this convention. It's going to save you some errors in some confusing scenarios. So here's the problem. You have a boat, okay? Let's say you are sailing in a boat, and the boat's velocity with respect to water is given by this. But the water is like a river. It has a current like this. Okay. So what's the boat? So boat's velocity, okay, maybe I can zoom in to show it a little bit more clearly. Boat's velocity with respect to water is this. Water's velocity with respect to shore, like fixed point on the shore is this. And the question is, how can we write this? Okay. So that's what we want to do. Boat's velocity with respect to shore. I'll just give you a few seconds to look at the problem and think. So, okay, let me maybe write this one and ask you the second part. So it's like we, okay, are interested in boat's velocity. And what do I need? I know v boat's velocity with respect to water, which is a vector, plus v water's velocity with respect to shore, which is again a velocity. Here, let's pay attention to these arrangements here. I start with B on the left hand side, and on the right hand side, it also starts with B. On the left hand side, I finish with S. On the left hand side, I also finish with S. And please pay attention how these W's match, right? It goes from B to W to W to S. So if you keep your indices like this, like arranged, I think it is going to save you a lot of trouble in the future. Just try to write it like this rather than B, W, S, blah, blah, or like this. For example, imagine you are like a fisherman in the boat and you are walking like this, some V fisherman with respect to the boat. Okay, let's say this is given, fisherman's velocity with respect to boat. Can you write this fisherman's velocity with respect to shore in terms of all the others? What is the fisherman's velocity with respect to shore? Okay, I started to have some answers. VFB minus VBS. Okay, that's one answer. And we have fisherman with respect to boat, fish and boat with respect to water, and we have water with respect to shore. How should I start? I have F on the left hand side, so I want to start with F on the right hand side. V fisherman. Now the second one, I have fisherman with respect to shore, but I am given boat here. This is the first one, plus V, okay, I finished in the previous case with B, so I have to start with B. Boat, vector, and boat with respect to what? I have water, right? Now I finish with water, so I have in the next case V, water, and last one is S, okay? Please look how F is on the leftmost side on both sides of the equation, and S is on the rightmost side. So I start with F, I start with F, I end with S, I end with S, B to B, W to W. This kind of index matching is important. For example, you can do maybe I can. So if you see a sum like this, like VBW, VBS plus VWS, you can immediately tell something is wrong with this, right? So you start with index here B and B, that's fine. But this one does not match. And these internal indices, these guys also don't match, right? If you write something, if you find yourself writing something like this, just take a look and then say, okay, I must have done something wrong. What is wrong with this? And I can actually show you what is wrong with this. So if you write VBS, both velocity with respect to shore, right? This is VBS. And the second one, water's velocity with respect to shore, this is V water with respect to shore. And I am summing these two vectors, like I can sum this head to tail, and this sum vector V, it says VB water, but what is this? There's no velocity like this in that problem. This doesn't mean anything. Okay, just be careful. Finally, let me just say that this is also logical corollary. Like if VAB is like this, A's velocity with respect to B, you can switch A and B and put a minus sign. Basically, B's velocity with respect to A is minus of this. And that's, I think, logical, right? If I am moving with, I don't know, 5 with respect to you, you are moving minus 5 with respect to me. I mean, you just switch. So here are yours. Maybe there's no questions. Maybe I can start with some suggested problems. So here are your suggested problems. So let's V1 be this and V2 be this. Determine the magnitude and direction of V1, V2, V1 plus V2, and V2 minus V1. Okay. So maybe I can draw some pictures. Maybe how? Okay, this is V1. V2 is 4.5 along X, 1. So determine the magnitude and the direction of V1, V2, and okay. First magnitude, I think magnitude of V1, we just use V1 without arrow, and it's equal to 6 squared plus maybe 6.0 squared plus 0.0 squared square root is equal to, just calculate, 6 squared plus 8 squared is equal to, take square root is like, I think some of you know this kind of triangle, like 6, 8, 10. It's like 3, 4, 5. There are like special triangles like this, but you don't have to know it. You have the calculator. So, and the direction, I don't know, maybe we can calculate this called theta, and theta is this side divided this side, which is, I think, 8 divided by 6 is equal to this, and I want to take inverse tangent 8, and it seems like my calculator is telling me it's about 83 degrees. So we can do the same thing, V2 4.5 squared plus 5 squared. Okay, clear. 4.5 squared plus 5 squared is equal to, and square root is 6.7. Let's call this theta 1. I don't know, let's call this theta 2. Theta 2 is equal to tangent minus 1, 5.0 over 4.5, 5.0 over 4.5 is go to this and take inverse tangent is equal to, this one seems to be 48 degrees. You can see it from the geometry. Isn't it 8/6? Thank you. This is 8/6. Let me calculate this again. 8/6 and tangent to the, yeah. I think somehow I did the right thing with the calculator, but the wrong thing with the writing. That happens. So that's A. That's B. So C V1 plus V2 is equal to. So let's calculate X components. I think this is, I don't need a calculator for this. This is 1.5. Is that correct? Yes. Minus plus 3.0 J hat. Okay. So let me just, this one, yes, and this one 3. So it's like, maybe I can write it here. So 1.5 along minus X direction and 3 in plus 1, 2, 3. So let's use a different color for this guy, maybe green. Something like this. This one is V1 plus V2. Magnitude and direction, let's do this. V1 plus V2. I'll use this because I don't want to use another letter for this sum. This is 1.5 squared plus 3.0 squared. I think it's 1.5 squared plus 3.0 squared. 3.0 squared is equal to, and square root is 3.3. 3.3. Yeah, maybe 3.4, but that doesn't matter. And the angle, maybe I can show it with this theta 3 and theta 3. Does that make sense? Yes, it should be bigger than this guy. 63, 10 degrees bigger than theta 1. And V2 minus V1, let's do this too. A, B, C, D. V2 minus V1. X is plus, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something along here. And J is minus something, like magnitude is.
Professor, sorry for disturbing.
Uh-huh.
I think it's 10.5, not 10.
Oh, yes, yes, thank you. It's 10.5. Yes, thank you. So this is V2 minus V1. And if we take square root, actually 16.7. And the angle theta 4 maybe is theta 2, so that makes sense. And I can box all these guys in if you like.
Professor?
Put the angle so you know which direction you are looking. I think for this one, for example, your book says theta 1 is equal to 53 degrees. So this is north, this is south, this is east, this is west. So your book used the convention for this angle. It is 53 degrees north of west. So as long as you're unambiguous with your answer, I think that's fine. So do we have time for one more problem? This one is actually simple too, but maybe I can just show it and end here. And if you guys want to leave, that's okay. And we can just have like a chat for like 5-10 minutes. Okay, I think this is the end of lecture for now. If you want to leave, please feel free to leave. And if you have questions, I'll be here. We know that multiplying a vector with a constant, can we multiply a vector with another vector? You can multiply a vector with a vector, yes, but it is a little bit beyond the scope of this course. So when you multiply vectors, it's actually more complicated than these, and there are different ways of multiplying vectors. You'll learn linear algebra some point, maybe next year. And in the linear algebra, you'll see vectors are actually very special quantities. And you can, yes, multiply a vector with another vector, but that multiplication has to be very special. And there are actually two different kinds of vector multiplications. Maybe I can write here. So we can multiply, there's people generally use dot, and they call it dot product, V1 and V2, and they call this dot product. You can multiply two vectors with a dot product, and result is scalar. But that's not the only kind of vector multiplication. There's also like cross product. You can do a vector multiplication like this. They call this cross product. And the result, maybe I should write the result, is also a vector. This is actually very important. For now, I don't want to say anything else, but your answer, please hold on to your answer until your linear algebra class. And when you see things like this, don't be scared. They are actually rather nice things. I shouldn't talk about these in this class, but I couldn't help myself. And I'll see you guys next time. Thanks for coming today. Okay, take care.